Hi, welcome back. This is lecture 11. We're searching for more characterizations of valuation rings. So before I do that, I'll just recall some more facts from ring theory. Suppose you have two rings. There are local rings. Let's say maximal ideals M1 and M2. We'll say a ring homomorphism from R1 to R2. Let's call it phi. It's a map of local rings. If it takes the maximal ideal of R1 to the maximal ideal inside the maximal ideal of R2. So if phi of M1 sits inside the maximal ideal of R2. And one observation is that suppose this map phi is injective, so R1 sits inside R2. Suppose phi is an injective ring homomorphism. So R1 sits inside R2, and let's just denote that by phi. Then the following are equivalent. So one is that phi is a map of local rings, and another way of stating that is that, well, we have the maximal ideal of R2, you can intersect that with R1, then you get the maximal ideal of M1. Okay, and so if you're in this scenario satisfying one of these equivalent properties, so in this scenario, we say that, so if you have this inclusion and it's a map of local rings, so we say that the local ring R2 dominates the local ring R1. Okay, so the setting is the following now for us. So let A be a domain with fraction field K. And suppose you have a local ring, say with maximal ideal MB, and suppose A sits inside B, and that's inside this field K. Okay, and just an observation that if B sits inside K and the fraction field of A equals K, then in this case, the fraction field of B also equals K. Okay. So our definition, so we say that the local ring B is maximal under domination inside K if whenever there is a local ring C inside K that dominates B, then C has to equal B. Okay, so just trying to unwind this definition, in other words, you just try to unwind the definition. So suppose C is a local ring with maximal ideal MC, and suppose C is inside K, and suppose C dominates B. So we have B sits inside C, sits inside K, and under this inclusion we have that the maximal ideal of C when you intersect with B, you get back MB. So if B is maximal under domination inside K, then under this hypothesis it just means that B equals C. Okay. So here's another property of a local ring being maximal under domination inside a field. How is that related to being a valuation ring? So the first proposition that we want to show is that suppose B is a valuation ring, then B is maximal under domination inside K. Okay, so what's the proof? So suppose B is a valuation ring inside K. So we'll use the characterization that if B is a valuation ring, then it's a V ring. So we use the characterization that B is a V ring inside K. And so if you have an alpha that's not 0 in K, then either alpha belongs to B or alpha inverse belongs to B. So now suppose for the sake of contradiction, that B is not maximal under domination inside K. So what does that mean? So then there exists a local ring C and let's call the maximal ideal MC. That sits inside K, the property that it contains B. So B is included in C. It's a injective ring homomorphism, and under this injective ring homomorphism, the maximal ideal of B sits inside the maximal ideal of C. Okay, and our assumption for the sake of contradiction is that B is not maximal under domination. So what this means is that this B is not in C. So in particular, there exists an element little c that's in the ring C but that's not in B. Okay, so you have an element that's in the ring C and not in B. I'm calling it little c, and so clearly it's not 0 because 0 belongs to B. And now since B is a valuation ring, in particular it's a V ring, so you have this element C, little c, so this either little c belongs to B or its inverse belongs to B. Okay, but by assumption, since little c does not belong to the ring B, we must have that its inverse, C inverse, belongs to B. Okay, so again, so now we have this element C inverse in B. Now the observation is that this element C inverse belongs to B but is not a unit in B. Why? If C inverse is a unit in B, we have an element let's call it D in B with the property that C inverse times D equals 1. But you also know that C inverse times C equals 1. And so just cancelling off C inverse on both sides, we get that D equals C. Okay, so on the one hand, you have that D belongs to B. On the other hand, you have that C by our assumption does not belong to B. So the only possibility is that this observation is correct, that C inverse is not a unit in B. So C inverse is not a unit in B. So since B is a local ring, C inverse is not a unit there, so we must have that C inverse belongs to the maximal ideal of B. And thus, so we have that B sits inside C with the property that the maximal ideal of B sits inside the maximal ideal of C, and we have this element C inverse which belongs to MB, and so it must belong to MC. So C inverse belongs to MC. Okay, and now since C is a local ring and you have an element that belongs to the maximal ideal, what we have is that C inverse is not a unit in C. But this contradicts the fact well, C inverse is a unit because C inverse times C equals 1, where C inverse belongs to B, so it belongs to C. Little c by our construction or our choice belongs to the ring C. So we have these two elements that when you multiply them out, you get 1. And so we have a contradiction so the only possibility is that our assumption that B is strictly inside C, so this assumption has to be incorrect. And so this proves the proposition that evaluation ring B is maximal under domination inside K. So if you have a valuation ring then it has this property that it's maximal under domination inside K. And now I want to ask the converse. If I have a local ring that is maximal under domination inside K, is it a valuation ring? So I want to prove one proposition that helps in proving the converse. Suppose I have a ring that is a local ring that is maximal under domination inside K, then B has to be integrally closed. Okay, so what's the proof of this? You take an element alpha in K and suppose it's integral over B. And now suppose for the sake of contradiction, that alpha does not belong to B. So we have an integral extension. So B, we have B of alpha, and you have this ring map phi, and everything sits inside K. And so now using the going up theorem from lecture 6, so B is a local ring, so there exists a prime ideal Q lying above MB. So MB is a maximal ideal and hence a prime ideal. So if MB is a maximal ideal of B, it is also a prime ideal of B. And we have this integral extension. And so if you remember, you have this integral extension. And so the going up theorem or lying above theorem holds, so you can find some prime Q lying above MB. Okay, so in particular, MB sits inside Q. And now to get a local ring, you can localize. So let SQ denote all the elements in the ring B alpha minus, but you don't include Q. And now you consider the local ring C that's given by this localization with respect to this multiplicatively closed set SQ. So let C denote the local ring SQ inverse B alpha. So it's a localization of B alpha with respect to this prime ideal Q. And this has its maximal ideal is the localization of SQ. Okay, and so call this maximal ideal as MC. And so we have inclusions. So B sits inside B alpha, and that sits inside C, which was this localization, and everything sits inside K. And B was a local ring, and because the extension B to B alpha is integral, we found this prime ideal Q with the property that MB sits inside Q, and Q sits inside MC, which was this localization of Q with respect to SQ. And so what do we have? We have this inclusion of local rings B to C, with the property that when you look at the image of the maximal ideal B, it sits inside the maximal ideal of C. And by assumption, alpha belongs to C because alpha is inside B of alpha, which sits inside C. So alpha is in C, but by construction alpha, or by assumption, alpha was not in B. And so thus C strictly dominates B inside K. But this contradicts the fact that B is maximal under domination inside K. So the only possibility is that this element alpha, which was integral, has to belong to B itself. So the only possibility is that B must be integrally closed. Okay, so this proves the proposition. So we'll use this proposition next lecture to show that if you have a local ring that's maximal under domination inside a field, then it's a valuation ring. Thank you.